Hello. This video will have to do with defining the absolute value. The absolute value, denoted by these bars, of some x, mathematically is defined as a piecewise function, meaning it's defined in different pieces. The first piece is x. The absolute value of x is really x if the value of x is greater than or equal to 0, and it's negative x if the value of x is strictly less than 0. Okay? So what does this mean? Well, I've heard the absolute value as being the distance away from 0. I've heard of people defining the absolute value as that. And actually, that's a very good definition because, well, take negative 3. Absolute value of negative 3, as you know, is 3. Furthermore, take positive 3. Absolute value of positive 3 is 3. So notice that it's true, because the distance here is 3. Negative 2, negative 1, 1, 2, and the distance here is also 3. So to think of the absolute value as the distance away from 0 is a wonderful way of thinking about it. All right? But now, we'll be able to think about absolute values, and we're going to be able to solve equations having to do with these absolute values. All right? Or we will be applying this definition. So, for instance, let's use an equation. Let's say the absolute value of 2x minus 3. Let's say this equals 5. We want to solve for all the x values that make this a true statement. All right? Two things we got to do. We got to do the plus case when this whole thing in the inside is positive, because the absolute value definition implores us to do so. So we assume that 2x minus 3 is equal to 5 in the positive case. In the negative case, we must do the opposite. We suppose that the inside is negative, okay? So that means the whole shebang here on the left-hand side is negative, and we set that equal to 5. In both cases, we algebraically solve for x, and we're done. We found all of the x's that satisfy this equation. Let's take a look. Solve here. I add 3 to both sides, plus a 3, plus a 3. I get 2x is equal to 8. Then I divide by 2. X is equal to 4. This is one of the answers. Over here, I divide by negative 1. I get 2x minus 3 is equal to negative 5. I add a 3. So I get 2x is equal to negative 2, because I added a 3. Then I divide both sides by 2, and I get x is equal to negative 1. Let us check. Let us quantify the veracity of this statement. Okay? Here's our check. And you should always check, not only as a good exercise for yourself, but in order to make sure you didn't make a mistake like on an exam. You should be able to check yourself, and you should know that you did it correctly. So I'll plug in this 4 and see if this works. Does this indeed equal 5? Well, that's absolute value 8 minus 3. That's equal 4, 8 minus 3. That's 5. Check. Now, this is for 4. Now let's check it for negative 1. I'll put in 2, and 1 minus 3. That's equal to absolute value of negative 2 minus 3. This is absolute value of negative 5, which is a 5. Check. So in both cases, it worked. That's a good sign, all right? That means I didn't make an algebraic error. But even if you do, it happens to the best of us, and you shouldn't be crying about it too much. Just put the work in and check yourself. Okay? Let's do another example. Let's clear up some real estate here. All right? Let's do a slightly more complicated example. Let's do something like 2 times 3x minus 1 plus 7 is equal to a negative 3. All right? We can't just apply the absolute value definition like earlier. This only works when the absolute value is all alone. So let's make sure we isolate this piece first. And to do that, we gotta send this positive 7 packing by subtracting it from both sides. So that's negative 3 minus a 7. I know that. That's negative 10. Now to almost set up the absolute value definition, I have to divide both sides by the number 2. Divide by 2, divide by 2. Now I get 3, absolute value of 3x minus 1 is equal to negative 5. Now we can apply the absolute value definition here. In the positive case, I just get the 3x minus 1, which is what's inside the bars, is equal to negative 5. And in the negative case, I get the negative of that. Negative of all of 3x minus 1, put parentheses around it, is equal to negative 5. Alright, here in the positive case, I solve for x, so I add 1 to both sides, I get 3x is equal to negative 4. That means x is equal to negative 4/3 upon solving algebraically. Over here, I divide both sides by a negative, so I get 3x minus 1 is equal to negative 5. Then I add a 1 to both sides, I get 3x is equal to negative 4. Divide by 3, I get x is equal to negative 4/3. X is equal to negative 4/3, x is equal to negative 4/3. This is easy to check, right? Because we just got to check it for 1 since they're both the same. So let's see. 2 times 3 to the negative times the negative 4/3 minus a 1 plus a 7. Does this equal negative 3? We'll see. So this is equal to 2 times the 3's cancel here, so I just get a negative 4 minus a 1 goes to absolute value plus a 7. Alright, this ends up becoming negative 5. Once you absolute value negative 5, that's 5 times 2, that's 10. So I get 10 plus 7. This is equal to 17. This does not equal a negative 3. Okay? What's going on here? Alright? The fact that we got a contradiction like this means that there is no such x that satisfies this absolute value equation. So, there is no x's that, if I were to pick them, I would get that to equal a negative 3 on that side. That makes sense. What if x was 0? Well, I would get 2 times 1 plus 7. That's not a negative 3. Well, what if x was negative numbers? Well, I don't know. I could make x a negative 30 or a negative 10. Take a look. This would become negative 30 minus a 1. That would be negative 31. All right. Absolute value, it becomes positive. So the left-hand side is always positive because even when we plug in negative numbers, the absolute value changes its negative property and turns it positive. So it seems like there's no x that satisfies this because our solution method showed us that our only 2 possibilities was negative 4/3. We checked that and we saw it leads to a contradiction. 17 does not equal negative 3. So there are no solutions. Okay? Let's do another case. Grab some real estate. Let's do absolute value of x minus 3. When does this equal, well, let's modify this slightly. That's too easy. 2 minus a 1. When does this equal, let's say, a 15, all right? Let's check this one. Again, we can't apply the absolute value yet. We have to add 1 to both sides. Okay? Then we got to divide both sides by 2. Half of 16 is 8. Okay? Now I apply my absolute value definition. The positive is x minus 3 is equal to 8. The negative is all of this, x minus 3. Put a negative in front of it, is equal to 8. Over here, I just add a 3 to both sides. 3 plus 8 is 11. Put a box around it. Over here, I divide both sides by negative 1. Negative 8. I add a 3. That means I get x is equal to be negative 5. Now let's check. Does x indeed work? 2 times absolute value of 11 minus 3 minus 1. Does this equal 15? Well, 11 minus 3 is 8, correct? Then 2 times 8 is 16 minus the 1, that's 15. That worked. Now what about this negative 5 here? 2 times absolute value of negative 5 minus the 3 minus the 1. Negative 5 minus 3 is negative 8. Absolute value, that becomes positive 8 times 2 becomes positive 16. This is 16 minus a 1. That is equal to 15. Check. These work. So don't be surprised when sometimes it works and other times it doesn't. Whenever you solve it, like in the last problem, whenever you solve these and it leads to a contradiction, like something like 17 is equal to 5, then you know that there does not exist an x value that can be chosen that will solve the absolute value equations.